We will be studying exact type of ODEs today, and ODE is exact, is of type exact if this ODE has a solution u of xy is equal to a constant c. This means that if we compute its total integral, its total differential partial u over partial x plus partial u over partial y dx plus partial u over partial y dy, it becomes equal to 0 because the derivative of a constant is 0. So we give this partial u over partial x another name, we call it m, plus call it n dy is equal to 0. So if we have a differential equation in the form like this, m, where m can be a function of x and y, n with n can be a function of x and y, m times dx plus n times dy is equal to 0. This can be presumed to have a solution like this, but it has to follow and it has to fulfill another necessary and sufficient condition. So given a differential equation like this, we have to first check what the necessary and sufficient condition. Only then we can claim that it has a solution like this, u of xy is equal to c. What's that check? What's that condition? Right, given this m, if we compute partial m over partial y, since m is partial u over partial x, that would be partial over partial y of m, that is partial u over partial x, right? So this becomes partial squared u over partial x partial y. Let's call it equation number 1. Given this n to be equal to partial u over partial y, let's differentiate it with respect to x. So this becomes partial u over partial x, n is equal to partial u over partial y. So even this becomes partial squared u over partial x partial y, equation number 2. We see the right hand sides of equation number 1 and equation number 2, they are the same, exactly the same. Therefore we conclude that partial m over partial y is equal to partial n over partial x. This is that necessary and sufficient condition, this one. So we will be given an equation like this in this one, and we think that its solution would be this, u of xy is equal to c. But to be confident, we have to first check the necessary and sufficient condition. We call this m, this n. We call this m, this n. And we differentiate m with y, we differentiate n with x. And if they come out to be equal, then this is an exact type of ODE, ordinary differential equation. And once we have established that necessary and sufficient condition, we know the solution straight away. Partial m over partial y is partial n over partial x. If this is true, you have to check if this is true. If it is true, what would be the solution? M is partial u, you have put m is equal to partial u over partial x, or you have put n is equal to partial u over partial y. So m is, so from here we can write u is integral m dx plus some function of phi, or from this equation you can write u is equal to, or from this equation you can write u is equal to integral n dy plus L of x. So you can use either this equation number 3 or equation number 4. They both will give you the answer of this, or both will give you this u of x, y. So the steps are, given an equation like this, where we have a function being multiplied with dx and a function being multiplied with dy. This m can be a function of xy, this n can also be a function of xy. M is being multiplied with dx, n is with dy. You have to check the necessary and sufficient condition by differentiating m with y, n with x, and if it is true, you'll say, okay, it's an exact type of equation, this is the solution, either this is the solution or this is the solution. So it's that easy. And of course then we have to, if we consider this as solution, we have to find k of y, and if we consider this as solution, we have to find L of x, and we can do that very easily. So given this basic information, that the exact type of what is the appearance of an exact type of ODE, how would you check the necessary and sufficient condition, and what would be your solution? Given having these three pieces of information, now we are ready to solve an example. So you have to keep in mind that then first you have to, given an ODE, you have to check the necessary and sufficient condition first. That would be your first step. And then after that, you would be having the solution either using equation number 3 or using equation number 4. So it's very easy. So given a differential equation ODE, first order ODE like this. So we are given an equation like this. Is equal to 0. So assume this to be m and this to be n, but we are not sure right now. We are not sure that whether it is an exact type of ODE or it is not. So we have to first check the necessary and sufficient condition, that is partial m over partial y. That would be, for cos of xy, that would be minus sine of x plus y times the partial derivative of x plus y with respect to y, that is 1. So, and for partial n over partial x, that would be 0, 0, because they are not function of x, plus that would be minus sine of x plus y, and partial derivative of x plus y with respect to s would give you of 1. So even this is equal to 1. Even this is equal to sine plus xy minus sine of x plus y. So since partial n over partial y is the same as partial n over partial x, it is an exact ODE. So what's the solution? Step number 3. What is the solution? So given, it's not step number 3, it's step number 2. So given this equation, step number 1 is to check the necessary and sufficient condition. Step number 2 is your solution. Straight away, the solution is, we wrote two kinds of solution. Either u is equal to m dy, m dx plus k of y. Either this can be a solution, or this can be a solution, because we have put u is equal to partial m, we have put m is equal to partial u over partial x. So we can use any of these two, 3 or 4. So let's use 3. So u is m is minus sine of x plus y plus k of y. So the integral for minus sine is minus cos, so this is cos x plus y plus k of y. So this is u equal to, but this u involves another variable k. So how to do that? We know that if we, that's straight away, that's very simple. You have to integrate partial u over, n is partial u over partial y. So partial u over partial y should be equal to n. So what is partial u over partial y? Cosecant of xy is its derivative is minus sine of x plus y plus partial k over partial y is equal to n, 3y squared. Plus 2y plus cos of x plus y. So there's a mistake here. M is cos here. It's cos of xy, and this is minus sine of xy. So there's a small mistake. Cos of xy. So we actually have to put m. So m is cos of xy. And its integral would be minus sine of x plus y. And we have to put here partial u over partial dy, and that is this plus partial this. So these two cancel, and partial k over partial y is 3y squared plus 2y, or k can be written equal to 3y cube over 3 plus 2y squared over 2 plus some constant. So now we are ready, because we have computed k, that is y cube plus y squared plus c static. So now we are ready to write the answer. Your solution, your answer is u of xy is minus sine of x plus y plus k of y, that is y cube plus y squared plus c static. And of course we started with the point that u of xy would be equal to a constant k or c. So this can also be written as minus sine of x plus y plus y cube plus y squared not minus, because integral of cos is sine, plus y squared plus is equal to k minus c static. So this can also be written as sine of x plus y cube plus y squared. This k minus c static can be written as c. So this is your solution. So actually this is the point we started with. If we differentiate this u of xy with respect to x plus differentiated with respect to y, that would be the same as we started. That would be our starting point, the differential equation we were given in the start. Right. So this is one of the questions we solved. We solved yesterday, and we have solved it again today. So the other problem, there is one other problem that we solved yesterday, and we are going to solve it today again. Another simple example, and that is that is cos y sine hyperbolic x plus 1 times dx minus sine y cos hyperbolic x dy is equal to 0. So let's check whether this is an exact type of ODE or it is not. So what we have to do is we'll assume this as m, we'll assume this as n. We'll differentiate partial m with respect to y. Partial m over partial y would be sine hyperbolic x would be a constant, and the derivative of cos y is minus sine y, and partial n over partial x, this is sine y, and it is a minus here, already it's a minus, this minus should also be included. Sine y cos hyperbolic x, the derivative is sine hyperbolic x. So we get minus sine y times sine hyperbolic x, whereas this is minus sine y sine hyperbolic x. Wow, partial m over partial y is the same as partial n over partial x, so it's an exact type of ODE, and we know the solution. So we don't have to solve anything. Once we have established that the two are equal, it's an exact ODE, and now we are going to write the solution. The solution is m dx plus k of y, or u is integral of n dy plus L of x. So if you use this as solution, this is minus, we'll write cos hyperbolic x out of this integral because it's a constant compared to y, sine of y dy plus Lx. So minus cos hyperbolic x, and the integral of sine y is minus cos y plus L of x. So this is cos of y cos hyperbolic x plus Lx, L of x. So this is a solution u, but we have to find L of x. For that we'll differentiate it with respect to x. Why with respect to x? Because we know that m is partial u over partial x. So partial u over partial x should be put equal to m. So if we differentiate it with respect to x, this is cos y, and cos hyperbolic x, its derivative is sine hyperbolic x, plus partial L over partial x is m, that is cos y sine hyperbolic x plus of 1. Right, so these two cancel, and partial L over partial x is a 1. This means L of x is x plus c steric. So now we are ready to write the solution. U of xy is cos hyperbolic x cos y plus L of x. This is what we have just derived. So putting L of x here, L of x is x plus c steric, and this must be equal to of 1 because this is our starting assumption, that we started with a function that was differentiable and was equal to 1, and that generated the differential equation, the exact type of differential equation. So we can also write it as u of xy is cos hyperbolic x cos phi plus x is equal to k minus c static, let's call it c. So this is the general solution for this differential equation, but we are in the question, we are given an initial condition. We are also given an initial condition. And that is y of 1 is equal to 2. This means when x is equal to 1, y is equal to 2. So let's put this in this equation. Cos hyperbolic of 1 cos of 2 plus x is 1 is equal to a c. So c comes out to be 0.358. Using calculator you can compute this value and this value. So this is 0.358. So this is your particular solution. By putting initial conditions we converted this general solution into the particular solution, and then we can plot it like this. If we plot it, this would be x, y. You can plot it like this. How would you plot it? You will try different values of x, and for one value of x you will try different values of y, and we'll put this for one value of x you'll plot different values of y. So this is x versus y, this is u of xy. U of xy would be plotted like this. So that's all for this lecture. In the next lecture we will study how to convert a given equation that is not exact, but with some integrating factors we can convert it into an exact form, and we will solve some examples from circuit analysis. Thank you.